If you recall, we decided to present the function call and return implementation using 3 different units, and we already went through the preview of what we want to do. We gave sort of an informal runtime experience of the function call and return in action. And in this unit, we are going to actually describe how we're going to make it happen, how we're going to implement it. So let's get started. Well, we begin with some VM code, which is quite arbitrary and uninteresting, and yet we're going to use it to illustrate a few things. So we have a function called foo.main and another function called bar.mult. And we assume that these functions emanate, or they come from presumably 2 different classes, right? I mean, VM code, as I explained several times, is something which is typically written by compilers. And therefore, it is safe to assume that if this is compiled Jack code, then the compiler was applied to a directory that included 2 different class files named foo and bar. And foo and bar had at least one function written in them, and we see these functions here, foo.main and bar.mult. And we see that at some point in main's code, it computes this expression that we see in the comment. So it pushes 19, 3, it calls bar.mult, and then bar.mult does some work and pushes a return value and returns. So there's nothing really new here, except that I emphasize the fact that a function may well call another function which historically belonged to a different class, but once everything is compiled into VM code, we lose this notion of classes, and what we get is just a long list of functions that have full names, which is the class name dot function name. All right, so we have a caller and a callee, and that's the typical situation that we discussed, and we have the typical function call and return commands that we are dealing with all the time. And here is the contract by which these 2 parties must play. So let's begin with the caller's view of what is going on here. Before I call another function, I must push as many arguments as the function expects to get. So, if I call square root, I know that I have to push 1 argument. If I call mult, I know that I have to push 2 arguments, and so on. So the assumption is that whoever wrote this VM code, whether it's a human being or a compiler, well, he knows what he's doing, so he knows how many arguments to push. Next, I invoke the function by saying call function name nargs, whereas nargs is the number of arguments that I pushed before. After the called function returns, the argument values that I pushed before the call are going to be replaced with the return value that always exists. So I know that when the function returns, something new is going to be at the top of my stack, and this something new is the return value. After the call function returns, all my memory segments magically are exactly the same as they were before the call, except that temp is undefined, and some values of my static segment may have changed because the static segment is visible by all other functions in the application. So it may be that some function that I called, or functions that were called by the function that I called, changed some statics, and that's just fine. All right, now what is the contract from the callee's perspective? Let's see. Before I start running, my argument segment has been initialized with the argument values that were passed by the caller. I don't care how, I just know that it's there and it's available to me. My local variable segment has been initialized, and all my locals begin with zeros. Once again, I don't care how, but it's there. My static segment has been set to the static segment of the class to which I belong. And since it's a compiled class, it's the VM file to which I belong. Memory segments, this, that, pointer, and temp are undefined upon entry. My code may well use them, but it's responsible to store some sensible values in them in case I intend to use them. And finally, my working stack is empty. One more thing that is very important in the contract is that before issuing a return command, I hereby agree that I'm going to push a value onto the stack. So once again, we see something that we said several times. The function must return something before it returns. Now, must push something onto the stack before it returns. Now, think about a situation in which this function began its life as a void method. Now, suppose it was a void method or a void function at the jack level. And void functions are not supposed to return a value. And we just said that you must return a value. Well, indeed, this is the case. Even if you're a void function, you must return a value. So you push something, you can push 0. And it's the caller's responsibility to do something with this return value. So if the caller knows that he called a function which is supposed to be void, it can simply toss away the value that was returned by the callee. If you didn't completely understand what I said here about this observation about void functions, then don't worry about it. We'll get to it again when we talk about the compiler. So we described the function call and return protocol from the perspectives of the caller and the callee. And now we turn to describe the perspective of the implementation, which is the third party in this dance here. Now, one way to realize a VM implementation is to write a VM translator. And a VM translator is a program that reads the VM code and translates it into assembly. And in our case, it's a heck assembly. And so the VM translator will go through the code and focusing on the function commands, it will, for example, when it reaches the call bar malt2, it will generate code that realizes this call. When it gets to the function command, it will generate code that realizes the function. Same with the return. And what we'll do from now until the end of the unit is that we'll zero in on any one of these things that I just described, and we'll explain what exactly the VM translator does. Now, the big picture is that the VM translator is going to generate code that, reading what is written here, it's going to save the caller's state, the state of the foo.main function. Then it's going to do a few more things to set up for the function call. And finally, it's going to say, go to the name of the function. So presumably, the VM translator at some point will generate a label which is the name of this function. And indeed, if you take a few more lines down the target code, you will see the label bar.malt. So this is how we represent the entry point to a function in assembly, in the translated assembly code. All right, so now we're going to explain exactly what we have to do with this pseudocode here on the right. So let's see, handling a call. We begin with some global stack that includes all sorts of stuff. And it also, obviously at the tip of the stack, we see the working stack of the current function. So the caller, the current function, is doing all sorts of things. And then all of a sudden, we encounter a call some other function command, and we have to we have to implement this command using assembly. What do we do? Well, since the call command includes the nargs parameter, we know exactly how many arguments have been pushed before, right? Nargs. So we know how many, how many of the values on the stack are actually should be treated as arguments. And here is what I do. Okay, the first thing is I push a label onto the stack, and later on I'm going to use the same label as the label to which I'm going to return after the called function terminates. So let's keep this in the back of our mind. I push some label that I generated. We see it on the stack now. Then I push LCL to save the state of the local segment, my local segment. I push my arg, saving the state of my argument segment. I push this, I push that, and then I reposition arg. Now let's think about it. Arg should be repositioned for the called function. Now, where should we reposition arg? Well, obviously, we should reposition it at the beginning of the arg segment, which is right here, right? Now, where is this address? Well, I can calculate it because I know how many things I pushed. I pushed 5 values, so I do sp minus 5. And then previously, the caller pushed narg's arguments, so I know exactly where to position arg for the called function. Then I do LCL equals SP, and that's where I'm going to start to push the local variables of the called function, so that's just fine. And finally, I go to execute the called function. Okay, so I go to execute the called function by simply writing the command in assembly, go to, and the name of the called function. And now I do something very tricky. I insert into the generated code stream the label that I pushed before, right? Remember, I generated the label. I gave it some agreed upon name that I have to agree exactly, on all these things at some point. And then I push it. So first I generate it. First I generate it, I push it to the stack, and then later on I output it, or I emit it into the generated code stream. So that's exactly what I have to do in order to implement a call command. Now, just to explain what is going on here, this is pseudo assembly code, and you have to take this pseudo code and translate it on a piece of paper into actual heck code, should you decide to implement this thing on the heck platform. All right, moving along, we know how to handle call, so now I want to treat the function command, the command that signifies that a function begins in the code. So let's read the big picture. The big picture is such that, whenever we hit a function command, the first thing that the translator does is it takes the function name and generates a label. Okay, and this label will serve as the entry point to the translated assembly code of this function. And then we simply have to write some assembly code that handles the setting up of the function's execution. So let's see how we do that. Here's my stack, and the stack is exactly as it was after the call happened. Because remember, when do we hit a function command? We hit the function command always just after a call command, right? Call, and then I hit the function. So this is the same state as we had at the end of the handling of the call. And now we encounter the function name nvars, which inform how many variables, how many local variables the call function expects to have. All right, so what can I do? I can generate the following assembly code. First of all, I take the function name and generate this label, as I explained before, and I put it, I write it into the generated code stream, and then I repeat nvars time push 0, right? I know how many local variables I have to create, and so I create them. And I simply push as many zeros as necessary, and I basically build the local segment of the called function. And that's it, right? That's all I have to do, and now the function can start doing its thing. So it will do its thing, and at some point it will want to return, right? And this will happen in our example here. And now I have to handle the return command. So reading the big picture, I have to generate assembly code that moves the return value to the caller, reinstates the caller's state, and then does a go to foo's return address, which is the return value in the caller's code. If you look at the middle of the code pane of the generated assembly code, you will see this address there, right? foo $ret.1. So presumably, this is the return value that the VM translator created when it handled the call. If you recall, the call command involved generating a return address, and so I see that I go to exactly this return address. And the question, of course, is how do I know how to do it? And that's what you'll see in the next slide. All right, so the called function did some work, right? And it grew its working stack. A working stack includes all sorts of stuff that the called function created. And then I have a return command. Now, because everyone is assumed to play by the rules, I know that once I hit a return command, I know for sure that the value at the top of the stack must be a return value, because everyone plays by the rules, right? And a function must push a return value before it returns. So the next thing that I have to do is as follows. And this is a little bit involved, but it's really not terribly complicated. First of all, I'm going to create some temporary variable, which I call end frame, and I'm going to assign the value of LCL to it. So if you look at the stack diagram, you will see that end frame indeed points at the end of the frame in the host RAM. I mean, the stack is obviously stored in the host RAM somewhere. All right, now the return address must be the contents of the word end frame -5, right? So end frame, which is like LCL, if you go -5, you hit exactly the address of the return address, right? The address of the return address. Now I need the asterisk because I want to look inside this word, and this is how I get the return address, and I put it in yet another temporary variable, which I call RET-ADDR, return address, and I sort of put it aside for now. And I have to do all these things in assembly, right? All right, so the next thing that I do is I reposition the return value for the caller. Now, where should the return value should be? The return value should be copied onto arg0, right? And I already have a pointer that is located right on arg0, and this is the pointer arg. So I have to perform the pseudo command arg equals pop, because the pop is going to retrieve the return value off the stack, and then I take this value and I put it in arg. So the result, look at the stack diagram, the result is going to be this. I popped the return value and I copied it onto arg, okay, or to the address that arg refers to. All right, moving along, I know where the stack pointer should be. The stack pointer should be just after arg, because this is the view that the caller expects to get. The caller expects to see a return value and then continue to do his work. So SP becomes arg plus 1. And now I can begin to recover the various segments that I saved on the stack before. So that should be end frame minus 1, the contents of end frame minus 1. This should be end frame minus 2. Arg should be end frame minus 3. And LCL should be end frame minus 4. So I recovered all my memory segments, and finally I can jump to the return address. Where do I jump? I jump to the address that I retrieved before, that I popped from the stack before, and put it in the variable RETADDR. Okay? So this is the logic that I have to now implement in assembly. I mean, you have to implement in assembly when you write the VM translator. Now, another thing that I want you to notice is that once I've set SP below arg, I basically communicate implicitly that everything below SP is, it's just game, right? It's like, it's recycled, it's dead, it's irrelevant, because, the next push is going to override the memory location where SP shows, and then SP is going to be down, and then in the next push we'll do this. So, all the entire block, which is marked as recycled, is no longer relevant. So effectively, that's the situation that now the caller is going to see. The caller is going to see the return value at the top of its working stack, and the stack pointer is going to show to point at the next word in the memory. And that's exactly what we wanted. So we did it. We showed how to implement return. And basically, we showed how to implement every one of the function calling commands. So to recap, this is our global stack. And we showed how to generate the assembly code that, when executed, will end up building and maintaining this global stack during runtime. And we didn't give you the actual assembly code, but we did give you pseudo assembly. And this code, when you write it in heck, will actually do everything which is necessary in order to build this complicated world that we described in the last 3 units. And the last comment that I want to make, which I think is interesting, is that the code that I showed you is completely language and platform independent. So you don't even have to commit yourself to the hack platform. The specification that I gave you here is actually a specification on how to implement the VM, our VM language, on any given target platform. We didn't say anything about where this thing is going to be stored in memory, or how I wanted to, which assembly language I wanted to use. Use whatever you want. And this is important because we just gave a universal recipe for implementing our VM language on any hardware platform, any computer out there. But of course, in this course, we'll do it in heck, because simply this is the computer that we are playing with in this particular course. All right, so basically, up until this point, we implemented 3/4 of the language, and with this unit, we are now putting a check mark also on the function commands, and we are done implementing the VM language. In the next unit, we will add a few more technical details on how to do it on the hack platform, and I'll see you there.